Hey everyone, welcome to This Explainer. Today, we're diving into a super frustrating situation: why your building is boiling hot, your energy bills have doubled, and here's the kicker, why your HVAC equipment might actually not be broken at all. You know, every single summer, contractors get the exact same panic calls. But before you go and write a massive check for a brand new unit and completely ruin your summer budget, let's take a look at what's really going on.
We've all been there, right? You're sitting inside, just sweating, while the system hums along right above you. It's the ultimate summer frustration. The AC is clearly running, but it's just not cooling anything down. It honestly feels like a total catastrophic failure of the machine. I mean, what else could it be when the fans are spinning, but you're still sweltering?
Well, guess what? It turns out that almost all of these catastrophic feeling complaints actually boil down to just 6 manageable hidden issues. And we're going to investigate all 6 of them today. So let's dive right in and decode these cooling culprits that mysteriously show up every single season to wreck our comfort.
All right, let's start with culprit number 1, choked and frozen coils. This one completely subverts our expectations. You go to open up the air handler, expecting to feel this blast of hot air, and instead, you discover the coil is covered in a literal solid block of ice. No way, right?
Now, here is a massive misconception. People see that ice and they immediately assume, oh, the system must be working overtime because it's an absolute scorcher outside. It makes intuitive sense. But the counterintuitive reality, an evaporator coil actually freezes because it's not receiving enough heat. The refrigerant inside is specifically designed to absorb heat from the air passing over it.
And this brilliantly illustrates what I like to call the freezing domino effect. So when airflow gets restricted, say by a ridiculously dirty filter or maybe a slipping fan belt, less heat actually reaches the coil. That causes the refrigerant temperature inside the tubes to plummet well below freezing. As a result, the natural moisture just hovering in the air literally freezes right onto the coil's cold surface. And once that ice starts building, well, airflow gets even worse, temperatures drop further, and the problem just feeds on itself until you've got a solid, impenetrable wall of ice. So, the absolute crucial takeaway here is this: always, always fix your airflow before you even think about evaluating refrigerant levels. Because dirty filters or collapsed ductwork are usually the actual culprits. So many systems end up receiving completely unnecessary, super expensive refrigerant, all when the real fix was literally just restoring the airflow from the start. Okay, let's move outside to culprit number 2, the condenser coil. This component acts like the radiator of the whole system, rejecting the heat it absorbed from the building out into the atmosphere. But when it gets caked in layers of dirt, dust, pollen, and grease, it truly struggles. As our source material perfectly puts it, imagine trying to breathe through a heavy blanket while running a marathon. That is essentially what your condenser fan is attempting to do when it gets clogged up.
And trying to breathe through that heavy blanket of dirt causes some pretty severe mechanical symptoms. Your head pressure, which is how hard the system has to literally push to circulate refrigerant, spikes drastically. Because of that, your compressor amperage rises and your energy consumption absolutely soars, while your overall cooling capacity just drops off a cliff. The equipment might still be running and making noise, sure, but it's incredibly inefficient and you're drastically shortening the life of your expensive compressor. Seriously, a relatively simple cleaning routine with a garden hose can prevent a massive repair bill here.
All right, so what if the system is making cold air just fine, and the supply temperatures look completely normal at the unit, but certain rooms in your building still feel like a total sauna? This brings us to culprit number 3, and surprisingly, it has absolutely nothing to do with the refrigeration itself. Think of airflow like a delivery truck. If the refrigeration system successfully creates the cold air, but the ductwork, our delivery truck, breaks down along the route, well, the cooling simply never reaches you. The destination remains hot and you remain miserable, even while the equipment is running continuously up on the roof, just trying to compensate for the problem. Now, that delivery truck can be stopped by several hidden physical roadblocks. We're talking severely undersized ducts trying to push way too much air, collapsed flexible lines acting like a kinked garden hose, leaky ductwork just spilling cold air into the attic, or improperly adjusted VAV boxes, which are really just the dampers that control the air volume to specific rooms. You might even just have excessive static pressure, which simply means there's too much air resistance in the pipes for the fan to overcome. So occupants are constantly complaining about uneven temperatures, but the solution definitely isn't just making the air colder. To actually fix this, you can't just glance at the thermostat temperature and guess what's wrong. You really have to investigate the scene. You've got to pull out your tools,
measure the actual airflow volume, verify the fan performance, and measure that static pressure resistance. Taking actual airflow measurements often reveals the exact physical roadblocks that simple temperature readings just completely miss.
Moving right along, let's look at a totally different kind of discomfort. Why might a room read the absolute perfect 72 degrees on the wall thermostat, but still feel terribly sticky, with windows fogging up and gross condensation dripping from the ceiling vents? Let's check out culprits 4 and 5, humidity and short cycling. So, here's a brilliant fact about air conditioners that a lot of people don't realize. They actually do two vital jobs simultaneously. They remove sensible heat to drop the temperature you actually feel, but they also remove latent heat, which is the hidden moisture suspended in the air. When moisture removal fails, your comfort level completely plummets, regardless of what that digital thermometer says.
And here is the hidden trap in system design. If an AC unit is oversized for the space, it blasts the temperature down very quickly and then abruptly shuts off. It satisfies the thermostat's temperature requirement way before it has time to remove that sticky, latent moisture from the air. You're just left standing in a cold, clammy room, feeling like you're inside a damp cave instead of a modern office. This kind of rapid cooling leads directly to a highly destructive mechanical issue known as short cycling. Basically, the compressor violently starts up, runs briefly to drop the temperature, shuts down prematurely, and then restarts all over again just a few minutes later when the room warms up slightly. But a healthy, properly sized system, it should operate in nice, long, continuous cooling cycles to actually properly dehumidify the space. The cost of short cycling is huge. Each erratic start and stop places massive stress on the unit's electrical and mechanical parts. It spikes your energy bill every single time that motor kicks on. It guarantees inconsistent comfort across the building, and it drastically reduces your equipment's life expectancy. The fix here isn't just replacing burnt-out parts. You have to play detective to find the underlying cause. That could be oversized equipment, poorly placed thermostats, or even restricted airflow causing internal safety devices to constantly trip. Well, this brings us to the sixth and final culprit. And this is usually the specific complaint that instantly grabs management's attention: the silent energy drain. We're talking utility bills that suddenly go through the roof, even when the building feels reasonably comfortable to the people inside. The reality is that massive energy waste is rarely caused by one single catastrophic failure. Instead, it's this silent, compounding combination of multiple deficiencies deteriorating over months or even years. We're talking dirty coils, improper operating schedules running the AC at midnight, faulty temperature sensors, or failed economizers. And economizers, by the way, are just the mechanical dampers that are supposed to open and bring in free outside cooling when the weather is nice. You might even have systems that are simultaneously heating and cooling at the exact same time, literally fighting each other. The equipment just keeps running, but your efficiency is silently bleeding away. The solution here? Rigorous, ongoing measurement and utility data analysis. By regularly monitoring system performance, reviewing trend data, and verifying your control sequences, buildings often discover huge opportunities for massive energy savings. And the best part? You can usually achieve this without needing to replace a single major piece of equipment. As we've seen throughout this explainer, most summer HVAC failures do not start as massive breakdowns. They begin as tiny, misdiagnosed symptoms: a dirty filter, a slightly closed damper, maybe a failed sensor that no one noticed. It really comes down to troubleshooting over guessing. Because proper troubleshooting means stepping back. It's about understanding the complex but completely logical relationships between airflow, thermodynamics, and humidity control, so you can track down the actual, hidden root cause. It's about diagnosing the system as a whole, rather than just blindly throwing expensive new parts at a sweaty problem. So the next time your space turns into an absolute oven, just remember, the equipment itself might be perfectly fine, hiding the real problem in plain sight. Will you just guess and write another massive check? Or will you investigate the mystery like a true troubleshooter?